let's go ahead and pull out. So we remember all the names of our tiles, right? Like x tile, x squared tile, y squared tile, xy, 1 tiles, things like that. So if we pull out, go ahead and pull out an x squared tile, 3 x tiles, and 3 1 tiles. Now make the nicest shape that you can with like the nicest one solid shape. And we want blue to be up on all of them so we don't get confused that red is going to represent negative area. So red should not be up because it's going to represent negative area. We should probably go ahead and put a title on our paper since we're taking notes. So sorry I jumped into this too quickly. Let's write 1.2.3 on our paper. What we are doing is area as product and sum. Which you want to write that down so when you look back in your notes and you're looking for where was that area with product and sum type stuff, you can identify, oh yeah, that was this lesson. So this is actually the beginnings of how we can learn how to factor a quadratic trinomial. Fancy way to say 3 terms with x squared being the highest power term. Quadratic trinomial. So you should have out 1x squared, 3 x's, and 3 1's, which is already telling me who is goofing up what tile is what tile. Remember, the x squared tile is squared, not rectangular. So the thing that you should have 1 of out is the blue square, or teal, or whatever. I got some 7th graders wanting to argue colors with me, and my defense is normally just, look, I'm color deficient. 1 of these, right, which means the thing that we should have 3 of out is our x rectangle tile, because remember they are 1 in length, and 3 1 tiles. Now, has anyone figured out how we can nicely arrange these? Because this is a jumble. Anyone figure out how we can nicely arrange these? Now, one thing we'll notice about these tiles, I mean, if you could make a square is nicer than a rectangle, but if we can't, we'll probably just do a rectangle. So if I was going to try to do a square, I'd have to probably do the same each direction. Will I be able to go out the same each direction, having an odd amount of things? No, like a square would probably be pretty hard to create here. So what if I try to do, like, does that line up nice? And I threw this on graph paper to kind of re-support. These are non-commensurate. These are not actually countable. It looks like it's slightly longer than 4. We have no idea, right? Even though it looks like it's slightly longer than whatever. Well, these are centimeters, I believe. These are 5 centimeter boxes. Yeah, these are 5 centimeter boxes. But so it's not that this is 21 centimeters, right? Remember, this is we don't know. So that's okay. But does this line up, do the singles line up nicely on the X edge? Not really. Is there a better place that I could put the singles to line up? That would actually line up and like lock together. Don't the ends of my X's have a length of 1? So if I want things to actually line up, wouldn't it be better to put my 1s on the bottom of the X's? Because those actually line up. The X's are 1 wide. So go ahead and sketch this in your paper like this with the 1s on the bottom of our X's. Take a moment, sketch that. I'm going to line this up nicely. And then I want you to write out what the area is, the total area.
Was x squared plus 3x plus 3.
Yep. Just exactly what I told you guys to get out, right? X squared plus 3x plus 3. Now, what if I ask you to write the area as a product? Because this is a sum. If I ask you to write the area as a product, does that, like, I don't know, where got thoughts here? Man, I keep misplacing my binders. I have a feeling that we're maybe, I think I'm going to skip over this for now and come back to it, because I think I'm slightly struggling to communicate this well. Okay, what are we, never mind. I'm going to stick here for a second, because I need to get better. What are we missing to make this a nice shape, a rectangle? Like, what are we missing to make this a rectangle? This, if we had an X here, right, we would have a much nicer shape that we could then write out using its dimensions. How long would this rectangle be? X plus 3, not x squared. Be careful, because remember, the length is just x. So we could call this x plus 3. How tall is it? X plus 1, but we're missing an x tile. Right? Right? Because this, what I wrote in green, is everything inside of this box. But I don't have everything inside that box because I'm missing this. We're going to flip this process around. Grab out of your bag x squared, 8x, and 12. Let's see if this can work more nicely. It's using even numbers, so I'm already a bit more optimistic. Make sure that we're using blue sides. Plus 12. And that's a lot of constants to get out. Mine are all stuck at the bottom of my thing. Now you could get out a 5 tile, but that might not work as well as having individual tiles to move around. Once you have these singles out, I would advise keep them on your desk. Don't put them away until the end of class. Once you get done with A, try B, try C. Are there ways to make rectangles out of these? Because I don't know. I just tried the first one, and I think it's broken. Anyone think you can make a perfect rectangle with that first one? Eric, what do you think? You got a perfect rectangle yet? Now I see some of us trying something that is not going to work, and we should already know this from last year. It's okay if we need to review. Always totally fine. Should I try to line up an X tile on top of other X's? Like, should I put an X tile up here? No, because that automatically breaks my set. So my X edge should only ever go up against another X edge to keep things nice. So I decided I was going to try to make mine square. So I did 4 X's out, 4 X's down off of my X squared. But my 12 I'm still missing 4. Is there a better way to do this that we could actually line? Even if I move this over, I'm still missing. Well, now I'm only missing 3. Ooh, I was missing 4. Right here, I'd be missing 4. If I move this over, now I'm just missing 3. If I move one more over, and then wait a minute, I think that looks pretty darn nice. Who what? Well, I think what I have might be the only option. Do you have a different, does yours look different than mine? Ooh, now I'm excited. Okay, wait. I guess I should ask specifically, not just does yours look different, but is it different? Is really the question that I guess I need to ask. I'm pretty sure I can. No, I just want to copy this. I forget how to. I obviously haven't used this in a long time. All right. Let me pop over to you real quick. Go ahead and write down x squared plus 8x plus 12 like we have on our paper.
Ooh. Now the question is that different?
Let's do ours real quick, like this one real quick first, and then we'll do yours. So if I try to put this equal to its dimension, so this is your area as a sum, right? Something plus something, something plus something, a sum. What's my length of my rectangle? What's my width? So let's write that out. What this really is x plus 6. Sorry, not equals, times x plus 2. Now, this is where I keep saying, but is it different? Can I actually might just scoop yours up real quick, if I'm able to. Oh, it's on the actual desk. I don't know if this will work. Now, have you thought any more about is it different? Is the area the same? X squared, 8x, and 12. Yeah. Are the dimensions the same? Yeah. So, is this different? Not really. It's differently arranged, but it didn't really change anything. Because it's still x plus 3. And it's still x plus 2. Try B with 4x squareds and 4x's. I'm going to bring these back over to you, Danish. 4x squareds and 4x's. I think that looks kind of cool. I'm missing something, but I'm just getting creative up here. Anybody have suggestions to make it better? Because mine obviously isn't what I'm shooting for.
I mean, I just do like all the x's on the side, like vertically.
What do you mean? So how do I do the x squareds?
Just like the square,
Square?
and then just put the four x's like on the side vertically.
Like here, there. Oh, it's the same thing though. I'm still missing one.
Put the bottom two x's right next to the
Ah. What are the dimensions of this?
2x squared plus 2x.
What?
2x squared plus 2x.
The dimension? How long is this edge?
I mean 2x plus.
Ah, 2x plus 2. How long is this edge? So real quick on our paper, let's write down one thing this can equal. One thing this can equal is 2x plus 2 times 2x. But I think I can spot another arrangement. What if Yeah, I know, because I just walked past and saw yours and stole your idea. What if I do this? Is it the same tiles? Is it the same area? Is it the same dimensions? No. What are our dimensions now? What is this edge? X. What is this edge?
4x.
Yeah, 4x plus 4, because really I could rearrange this and scooch. So we need to write another option here that was a dimension of x by a dimension of 4x plus 4. So wait, is what we're saying then is x times 4x plus 4, that's equal to 2x plus 2 times 2x? Yeah, because 4x times 4 makes what? 4x squared. 4x times x. And over here, 2x times 2x. 4x squared. 2 times 2x. Oh, okay. Yeah. What's it called when we take an expression and break it into the pieces that can create it? If I take 20 and I break it into 5 times 4. It's the F word. Not that F word. No. Eric was like, wait, what? Factors! This is factoring trinomials, because you are currently factoring quadratic trinomials. Guys, there are college kids who can't do this. Now, will you always have algebra tiles in front of you? No. We're gonna have to learn how to do this without using algebra tiles, but understanding, first off, that quadratics, trinomials, are not some made-up, like, jargon nonsense. They represent physical items. A negative a negative variable value represents negative space, which is one of the most complicated ideas to think about, but that's why we use red here. Red is going to represent that if I have this much space taken up with negative and this much space taken up with positive, that area actually cancels. This is a zero area, right? That is actually a zero area. It is taking up space, but in the end, it actually is zero because the amount of negative area cancels out the amount of positive area. Try 2x squared plus 7x plus 1. This one has odd numbers. Let's see if we can solve this one. Oh, so all of that up here to say there are multiple factorable possibilities depending on what we're factoring. Because yes, they were equal to each other. 2x squared, 7x, and 1. Ooh, I think I'm starting to figure out where the extra tile could go. Maybe. Maybe not. Well, I don't know. That's what we're that's what we're using the tiles to kind of play with, right? See a couple of you starting to try, like, I can bring in an extra negative as long as I bring in an extra positive. Because that really doesn't do anything. Like, yeah, I don't know about this one, though. 2x squared plus 7x plus... I'm kind of stuck, like, staring at it like this and realizing I need more than 1. Right, no matter what way I organize my 7, it seems like... Because I can't put my x anywhere like down here. Because you might have the thought of what if I do a lot of these, but this, yeah, that doesn't work. Right, we said that's not allowed. Yeah, I don't know. Maybe we'll leave that one on the back burner for a second. What about the next one is x squared plus 2xy plus y squared. You want to see if that one works out? Try D. Try x squared plus 2xy plus y squared. Let's give ourselves a break from that annoying one. Yeah, you gotta go ahead and write that one down since you found out that it's actually factorable. Did we get D? I think most of us probably did. Look like that. And or probably turn 90 degrees. X squared plus 2xy plus y squared could then factor, what's the length of it? width of it? Yeah, this is x plus y squared, right? X plus y, the quantity, x plus y squared. Questions? All right, now the flip side. I want you to actually go ahead and put your tiles away, probably. I think that is everything we'll need the tiles for. Because I don't think you probably want to get out all the tiles to build this. Write this out first as its dimensions, then set it equal to its area as a sum. Okay, so first write out the dimensions, the product. Then let's write out the sum. Oh, I was getting this too. So guys, we are going to hop around a little bit. So like today we're doing 1, 2, 3. Tomorrow we're doing 1, 3, 4. So I'm hopping around a little bit to finish up this chapter. In my plan, unless something dramatic happens, is mastery on Friday. You guys will be ready. We will review on Wednesday. We will even play Jenga, because my high school mastery class always yells at me when I don't play Jenga with them, and I do with the other classes. So guys, your homework tonight is the 1.2.3 review preview questions in the book, or online book, right? Cool. 1, 2, 3. 1, 2, 3. Should be easy enough to remember, right? 1, 2, 3. Questions in the ebook. So if we go to write this as a dimension, or dimensions, Eric, help me out. What's the top dimension here? Yeah, 2x plus 3. Keep doing this. I don't like this thing. Dinesh, what's the, I don't know, the left dimension? I don't ever know how to say length or width or whatever. Careful, what is it? Remember, squared is only involved when we're discussing areas. This length is just x, right? So 3x plus just 2, if each of these are just 1. So how we would write this out is 3x plus 2 times 2x plus 3, and then that's equal to, leave a little bit of space, that's equal to, how many x squareds do we have in total? 6x squareds. How many x's? Yeah, 13x. How many ones? 6. Can anyone discern, like, length times width to find the area of a rectangle? Right? We're used to that. We've done a lot of that. This is just length times width, right? That's when the word just should not be involved. How in the world did we go from that length times width to that total area? Anyone like kind of see what happened? And there's actually a really nice shortcut that, of course, because it's math, we have an acronym for. So this is when it comes to, like, I don't know what you guys know or don't know yet. So this is where we involve the process called FOIL. But again, we all might not know that. So FOIL stands for, you want to hit us with it?
The prime.
Close, but I'll let that slide. First, outside, inside, last. Go ahead and on your paper out. First, outside, inside, last. Now the textbook specifically says, do not teach your students FOIL, but guess what? You're not the normal students. You're ready for this. What this really is double distribution. your 3x, and I'm going to color code this, your 3x is going to need to distribute to the 2x and to the 3, and that's going to be your firsts and your outside, right? So if we did this in order, I wouldn't just be doing these first, but I want it to make sense what we're doing. So what's 3x times 2x? 6x squared. 3x times 3. 9x. Now that is our outsides. Or no, yeah, this does still work. Sorry, because I actually drew this in the right order this time. Haha. So outside, 3x times 3, 9x. Now we go to the 2 getting distributed. 2 times 2x is the inside terms. 4x. 2 times 3. And when we combine our like terms, 6x squared plus 13x plus 6. If you are given the dimensions using 2 binomials, right? Binomials, 2-term expressions, binomials. This is how we multiply to find the product. We use the process called FOIL. Really, it's double distribution. FOIL just keeps track of making sure we did the right stuff. Questions on this? Now, Eric, because you took it over the summer, you got to be really honest if I move too fast on stuff. So, like always, you got to be honest with yourself. Have we seen this before? Eric? It's okay if you haven't. That's why I have a job. So go ahead and on your paper jot down area model. And I am still like retraining my brain to do it the correct way. Well, because you can do it completely flipped around. It doesn't actually matter, but they like to use left side and bottom. They used to use left side top, but I got to get in the habit of using left side bottom. So this is a better, in my opinion, better visual way to keep track of FOIL. Check it. Our firsts, our outside, our inside, our last. This is FOIL. Just drawn out so we can see it. So when we use an area model, here's the really nice thing about area models. If instead of a binomial, you had a trinomial that you were trying to multiply, you can use an area model to accomplish that. You can't use FOIL to do binomial times trinomial. I don't think there's a nice acronym word for it. I think it'd be funny to try to think up what it would be like. Because there'd be first, middle, last, first, last, right? Like, yeah. So try to fill in the empty pieces that may not even be inside of the area model. It might be outside the area model. So like for A, in order for x to have created 3x squared, what do we know about over here? That has to be 3x. Because 3x times x makes 3x squared. Then 3x times what would make 6x? 2. Try to fill the rest of these. We might run out of time and just have to start class with this tomorrow by like showing you the answers tomorrow. I will say I have more fun teaching you guys than just having you on Delta Math. I need to eat some lunch. because I always want to give you guys like an extra 30 seconds or a minute because you're way over here as opposed to being close to 8th grade. This is where we're going to run out of time for today. So we will pick this up tomorrow right here to make sure that we got right answers on this. And then we will keep rolling into the next new lesson, which will actually probably be 1, 3, 4, unless I change my mind tonight, because the other stuff we've pretty much covered. So if we look at what this chapter, if this will load, really has in it. So attributes of polygons, which we did, right? Predictions and investigating results, perimeters and areas of enlarging figures, so like scale factor versus scale factor squared. This is what we just did today, right? Describing a graph of like, is it increasing or decreasing, right? Is it linear, non-linear, all that sort of stuff. Angle pair relationships, which it looked like you guys knocked out on Delta Math when I checked the grades last night, so good work. Angles formed by transversals, again, we did that in Delta Math. More of that. This is what we're doing tomorrow. So the nickname for this is also known as the hinge theorem. And then closure. So if you look over at the board at the side of the room, you'll see I do have written up there our plan for the week. Right, 1, 2, 3, 1, 3, 4, the closure, then 2, 1, 1, just because. And then the mastery on the day when I am double booked. But we are actually going to try a new Friday schedule this week, I believe, unless it doesn't happen this week, where I won't be double booked. And I will actually have space for you guys when I actually teach you. So it might work out really nice, or it might crash and burn. Who knows? But yeah, now we are officially out of time, so I got to get you guys out of here. So thank you so much for stretching your brains with me. Have a wonderful afternoon. And your algebra tiles can actually stay at your desk. I think I'm using those in my next math class as well. But then I'm not actually going to wait around for you guys. I got to get